Is that what I think it is? A lot of people mistake wastewater treatment biosolids for something, well, a bit different. So what is that stuff? And where did all of the, go? Well, what you see here is sludge, or biomass. It ate the, reproduced, and then died. One primary purpose of a wastewater treatment plant is to accelerate nature, specifically to develop specific conditions to grow some special bugs. So what are these bugs? All of the bugs being grown in the wastewater treatment plant are natural and perform the same tasks, albeit in a little less dense populations, in water and soil around the world. The vast majority consist of various populations of bacteria who perform the bulk of the wastewater treatment process, such as BOD removal, nitrification, denitrification, phosphorus uptake, and so on. Generally, these bacteria are pretty boring to look at under the microscope. But not all the bugs are boring. Looking at a sample under the microscope will, in fact, reveal some other more exciting guys. They don't really contribute much to the overall process, but can play an important role in process control. So who are these guys? Let me make a note here that some of these guys will vary from process to process, so you'll have to get to know your own population. Let's take a look at a family called stalk ciliates first. Here we have a couple varieties that we're going to talk about. First is Vorticella. These guys attach onto a flock of bacteria and have a retractable tail. They can be pretty quick. Then there's Epistylus. Similar to Vorticella, Epistylus also uses his tail to latch onto bacterial flock formations. However, this guy's a little bit more passive and does not have the retractable feature, so he doesn't move around as much. Now to the family of the free-swimming ciliates. These guys also come in a few different varieties. Here's an Aspidisca. These little critters are easily identified by their many crawling legs. Say hello to Lytonitis. I don't know if I pronounced that correctly. And here is Trichophyllum. Look at this guy go. Ah yes, and rotifers. These are a higher life form with cool hairy mouths and are much larger than many of the other bugs we see here. Some forms are much more mobile and move around constantly. Others, a little bit less active. On our worm friends, the nematodes. These tiny worms, who can be active or just swimming lazily around the neighborhood, can also be an indicator of some certain conditions. Both nematodes and rotifers can be indicative of an older bacterial biomass and in wastewater are indicative of a higher degree of purification or seeding from an attached growth system. Another important bacteria to note are called filamentous bacteria. These include Microthrix parvicella, Nocardia, Thiothrix, and a whole bunch of other characters with no names but are classified as type blank 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 blank, like type 0914. As you would expect, filaments can also be used to identify conditions of sludge. There is a whole suite of indicator tests available to identify which kind are present in your sludge. So, do we care who's in our process and how many of them there are? Great question. The answer is yes. Here's why.
Researchers in England several years ago evaluated the presence of ciliated organisms in treatment plants. What they did was compare the effluent quality to the organisms that were present. And they developed a table which correlated which organisms were present based upon what the effluent quality was like. By identifying the filaments and by quantifying and tracking their presence, one can use that information to understand and identify the potential effluent quality you would see. For example, Vorticella and Epistylus are seen normally with high quality effluents, whereas Opiculera is seen more often in a lower quality effluent. This English study was updated to reflect the condition for nitrification in a wastewater treatment plant. And what they did was compare what particular ciliated organisms were present when nitrification was occurring and what organisms were present when it was no longer nitrifying. In this second study, a table was prepared and it showed the abundance of organisms that are more likely to reflect nitrifying conditions versus those that are present when non-nitrifying conditions occur. In all of these studies, it was stressed by the researchers and should be understood by anyone using this identification technique that the relative abundance will probably change based upon the specific operating conditions and the wastewater stream characteristics for each and every wastewater treatment plant. As such, the tables provide a good starting point, but should only be used as a starting point, and if one wants to be certain what's going on, they develop the table for their own facility. Using these studies, one can see that when you see critters such as Vorticella, when you see the shelled amoebas, when you see some types of rotifers, you see those only when there's low BOD present in the wastewater. That's not always the case, but it's usually an indication that those conditions are present. The best solution for any wastewater treatment plant is to do their own analysis, prepare their own table. And if you do that, you'll be able to use the stalk ciliates, the rotifers, and the amoebas to indicate what is happening and possibly predict the future of when it's going to change.
As previously touched upon, filament tracking can be another powerful tool to monitor conditions in a wastewater treatment plant. The abundance and type of filaments present can indicate various process conditions such as low dissolved oxygen, low F to M ratio, septicity, excessive grease and oil, nutrient deficiency, and low pH. Tracking filaments requires the use of staining tests, tests for sulfur granules, cell size, and presence of septa, as well as identification of attached growth on the filament. Jenkins, Richards, and Diager developed a chart to use in the evaluation process. With sufficient testing, the exact filament can be identified. The dominance of a filament indicates the operating conditions. If you want to change the biomass, change the underlying condition which supports that filament. For example, type 1701 indicates low DO, where type 1851 indicates a low F to M ratio. So what physical parameters could very well correlate with your microorganism populations? Well, the following list is a good beginning. SVI and settling rates, temperature, BOD, TSS and nutrient removal rates, dissolved oxygen levels, F to M ratios, wasting rates and SRT, mixed liquor concentration, pH, and the presence of pollutants. Once you identify and track indicator organisms, you can change the conditions you have control over, such as the mixed liquor concentration, aeration, RAS flow, pH adjustments, and nutrient deficiencies. It may take some effort, but it could help you do what you do better. And the better you operate, the cleaner the water is. And that makes it all worth it.